Hello everyone. In this video we will develop an adekoCAM door model from scratch. We have seen before how to derive new models out of existing ones as one of the easiest ways to populate a library, but of course in case you want a completely different model, you need to develop it yourself. And you can do this easily with the programming interface adekoCAM comes with in every installation. First, we will see the bare minimum form of an adekoCAM model and add new geometric objects to it step by step until it has its final form which matches with what we had in mind at the first place. Now let's go to the door interface and pick up on the minimum possible model, which has only the sizing layer, that is the empty model. Let me copy and rename it to door. Very creative. This is going to be our model we will be adding features to. Now we need to go to our model development environment, ZeroBrain, or to whatever your favorite Lua IDE is. This application is in the root directory of adekoCAM installation. We need to show where the Adeko Lua lib is before we start working. Only once for the first time. If you have already used this application to modify an adekoCAM model, this step could be skipped as ZeroBrain would remember the setting from the last time. I am pointing the Lua lib in adekoCAM root directory and go out. Now the development environment is ready. I'm going to the library directory and opening the script of the newly created model we named as door. This script is written with Lua programming language syntax. You can find quite a large body of information on this language, but don't worry, as it is not required to learn a new programming language to develop models in adekoCAM. I'll tell what each line means in this tutorial, and you won't need any other source to understand both model development cycle as well as the simple commands. An adekoCAM door model is basically a function named model main, and functions are written in between the function and keywords. Function keyword is followed by the custom name of the function and open close parentheses. A model returns true in case everything is fine and false in case of a mistake, such that an error message to the user can be generated. The double minus at the beginning of some of the lines means that those lines are to be ignored while interpreting the script. These are the commented lines we use to remind us things later or to give messages to the library user. If, for example, we remove these 4 lines, nothing will change. The model stays intact. It doesn't have any effect on the result. The keyword required at the end is needed for our code to run correctly in this development environment. This is needed to simulate user input such as the part dimensions we use to test whether or not our model is correctly parametric. Our door model here creates a single geometric entity, and that is the part shape, which is a rectangle and is generated on the sizing layer called panel. This rectangle sits at the depth material thickness as one of the known parameters in this environment, even though we didn't declare it explicitly anywhere in our script. This value would be set by the material selected by the user. These lines must exist in all the models you write, as every door model has to have a sizing layer and a binding rectangle or an arbitrarily closed shape to encapsulate various geometric objects within. Arbitrary shape part creation is visited in another video. Let's see what our model looks like. This green double triangle button runs the script. The result looks okay. There's only one rectangle as our part. I will create a door instance out of this model and send it to the project card. Then move the material to the second column and generate the cut plan so that we can see what the part looks like. Then I will move the job to the next column for toolpath generation. Following these steps, we will be adding new geometric features such as but not limited to edge chamfers, space filling patterns, sharp corner frames, notches, pockets, holes, grooves or channels, etc. to our model step by step, utilizing the simple set of adekoCAM math library commands. We will populate the project card with a single door having 500mm width and 700mm height after each modification to our model, such that we can observe the development history. Pressing this button here and moving the material to the second column to generate the cut list. The door has now a single rectangle. Moving to the next column to calculate the toolpath, creating a new procedure, and importing the only layer, selecting an operation, assigning a tool, and telling adekoCAM to get the depth from the object. I don't want to override it. Calculating the toolpath and observing that everything is okay. The depth and the shape is just fine. Let's get back. I'm moving the material back to the first column to give the plate we used for cut plan back to the plate stock such that it is not utilized. Every time you move a job to the first column, all the plates used in the nesting stage are given back to the stocks, a convenient detail. Going back to the development environment to start adding new features. Let's start with a simple rectangle frame around everything else. We will create a rectangle with a V-shaped tool having 90 degrees angle, 5 mm from the edges and at 2 mm depth from the surface of the material. So we will draw a rectangle. First we should set the name of the layer at which this geometric feature will be created. We do this with setLayer command. I'll name it as G_V90 so it will remind me that I should select GrooveCAM operation and a V-shaped tool with 90 degrees angle while setting up the procedure. Then we need to set the depth at which the geometric feature will sit. We do this with setThickness command. Now we can draw a rectangle at this depth. I'll need to give the bottom left and top right corner coordinate. The bottom left coordinates of this triangle would be 5, 5 because we want the rectangle to have 5 mm distance from the edges in both the directions. I wrote the top right coordinates in a parametric fashion because I want this rectangle to scale with the part dimensions. X is the width of the part and Y is the height of it. These are two of the known parameters within this script even though we didn't declare them explicitly, just like the material thickness is known as we saw before. Let's see what the model looks like. As you can see, the newly generated rectangle is added to the model. This basically is all we need to do to add new geometric features. Let's summarize what we have done in order to add a new geometric feature. 1. Provide a layer name after which all the geometric objects will be created on this layer until we change it. 2. Provide a depth after which all the geometric features will be sitting at. And 3. We create geometric features such as edge chamfers, space filling patterns, sharp corner frames, notches, pockets, holes, grooves or channels, etc. Let's now save some typing. adekoLib is a long phrase and we will be employing many functions from this math library, so it would be nice if we shorten this. I'm assigning this large name to the letter capital G and replacing all the long adekoLib phrases with this. This would save a lot of typing. Adding another door to the project card and see that everything is okay. Go to the toolpath view and import the newly added layer to the procedure, assign operation as well as a tool for processing. This way, as we develop our model step by step, its procedure will be maturing accordingly as well. As you can see, the toolpath for the second geometric feature is also generated. In case of a mistake, we would and should catch it here and correct immediately. Returning back to the development environment, and this time using a V-shaped tool with 150 degrees angle, I would like to create a sharp corner sunken frame 5 mm inside the rectangle we just created with 8 mm depth. I set the layer name as G_V150. Resetting the depth such that the sunken frame will be created starting from the surface of the material. As one of a few ways to create a sharp corner frame, I'll use sunken frame command from the library adekoLib, or equivalently now G. This command also wants the two diagonal points just like rectangle command, but in addition to it requires depth, meaning the depth of the sunken frame, tool angle and tool diameter parameters as well. This function checks whether the depth and diameter of the tool are in coherence, and in case of an error it fails. Let's see what the model currently looks like. A magenta colored rectangle with some other lines in it appeared now. This magenta colored shape is the sunken frame with sharp corners and is drawn in between two diagonal points just like the rectangle. The lines within it form the actual toolpath. Let's create another door and send it to the project card. As you see now, we have the sharp corner frame. Let's now create a toolpath. First, import a new layer we added in the model and then calculate the toolpath. The toolpath is successfully generated. I'm going back to the development environment, and this time let's assume we want to empty the middle part of the sunken frame so that it really looks like an elevated frame. So we want to create a pocket with 8 mm depth. Sunken frame function does not only create a sunken frame but also returns the two diagonal points of its inner rectangle to ease the utilization of functions requiring two diagonal points, such as but not limited to rectangle, pocket, plane corners, inclined pocket, etc. Let's first get these points from the sunken frame. The keyword local is used to define local variables which are only valid within the main function of our model. Here, bottom left and top right are 2 point variables, and we are assigning what sunken frame returns, the two diagonal points of its inner rectangle, so that we won't need to calculate them on our own. One of many ways to create a rectangle pocket is to use the command pocket from the adekoCAM math library, or equivalently G. This function also requires two diagonal points just like rectangle, but in addition to them, it also requires depth and tool diameter with which the pocket will be created. We will use a 12 mm cylindric tool for this purpose. Setting the layer name as G_12mm. Resetting the depth so that the pocket will be created starting from the top of the material, and using pocket function to create the new geometric feature. Something worth noting is that the depth parameter of functions like sunken frame or pocket and the depth we set with set thickness are cumulative. That is, they are added to each other. This must be interpreted like the following. Set thickness tells how deep the new geometric feature will be, and depth parameter of functions like pocket and sunken frame tells how high they will be, or their dimensions in the z-axis. As an example, here we say that our pocket is at 0 depth, meaning that it starts from the top of the material and it spans an 8 mm distance towards minus z-axis. Let's have a look at the model. A new visual appeared as a yellow rectangle with some dots in. This is the pocket entity. If I used 30 mm tool instead of 12, less number of points would appear and the model would require less time to produce. Create another door and add it to the project card. As you can see here, the pocket in the middle is created. Let's create a toolpath. Importing the newly added layer and making the assignments. Toolpath is in the right shape and depth. The magenta colored lines must correspond to what I had in mind in the first place. In case of a mistake, as a library developer, I need to go back and correct until these magenta lines are in perfect correspondence with what I had in mind. Going back to the development environment, let's tile a space filling pattern within the pocket. You can create your own space filling patterns from scratch or use already existing functions as starting points to do the same. Or the easiest, you can use the existing pattern functions as they are. We will use a simple meandering pattern, Menderes A. So we would like to add this space filling pattern 70 mm from the edges, having a width of 30 mm and a 2 mm depth starting from the pocket bottom. For this we need to use Menderes A function. You can use B, C and D instead of A as well. A has the simplest and D has the most complex form. This function takes as parameter distance from the edges and width of the structure both in X and Y axis. We will do this with a V-shaped tool having a 90 degrees angle. Since the depth is 2 mm from the pocket bottom, we need to set thickness to -10, which is going to be -8, the pocket depth, plus -2, the depth of the pattern. If you look at the model now, we will see the points generated for the space filling pattern. Maybe we can make it closer to the edges a bit, pulling the first parameters from 70 to 50 as the distance from the edges. Let's have a look at it once again. This time it looks better to me. Creating yet another door and sending it to the project card. As you can see, the filling pattern appeared on the part now. Going to the toolpath view. Since we didn't add a new layer for the newly generated space filling pattern as it is created on a layer already named, I can directly go to the toolpath creation step. Generating the toolpath and inspecting that the newly created feature is in place correctly. In this point, I need to follow the magenta colored lines as the toolpath, as they form the toolpath, but not the black ones. The machine code is generated according to the magenta colored lines, not the black ones. If you follow the black lines by mistake, you might think that the toolpath is incorrect. The lines are drawn with an apparent depth, not when we use set thickness to give the geometric object's depth, but when the points forming the lines have a non-zero z value as one of the coordinates. This difference is a detail not so important in many cases. Everything looks okay. Our model is complete. Now let's create a single door out of this model and perform CNC simulation and check if the resulting part is what we wanted. For this purpose, we will nest one part into a plate with the same size as the part, generate NC code for this plate, enter the NC code to the simulator, and inspect the final result against any mistake or features we would like to change, as in some cases there are aesthetic details which only become visible on the simulated part. You can use your favorite CNC simulator, or in case you don't have one, Geometrical is one of many easy to use open source good examples you can try out. adekoCAM comes with a simple post processor for Geometrical, and this post can be adapted to other machines as well, if not usable out of the box. So Geometrical, or whichever your favorite tool is, this tool is going to be your virtual machine. The best way to benefit from such a virtual machine is to make it identical to your actual machine by syncing their attached tools as well as their call IDs. This way you can check before actual manufacturing with no wasted time. This needs to be done only once, and you won't have to modify it until you make a change in the machine configuration. I'm now going to the machine setup to synchronize both the actual and virtual machines. Machine setup will be visited in another video in detail, so for now all we need to know is that we can select the machines on the left and mount the tools on the right by dragging and dropping the tools onto the available empty slots. I'm syncing both the magazine as well as the boring head if available. Once the sync is done, I am going back to the toolpath view and generate machine code or NC code. Now I'm saving the NC code just created, closing adekoCAM application, starting my virtual machine, which is Geometrical in my case, and mounting the tools with their correct call IDs, again only once. In my virtual machine, I'm importing the NC code we just created in adekoCAM, and I'm running the virtual machine. Here is the final form of the door. Everything looks okay. In case you want to change something, you need to go back to the development environment, make the modifications needed, and come back to this point to confirm the model is as you wanted and correct. Our model is complete and it is now usable, but as I remember, it's not final yet because neither we have a 3D model of it nor the model picture is in place. look, we cannot see what the model looks like in the library, or we cannot see its 3D model. We will fix this now, and we will be doing this only once every time we come up with a new door model from scratch. After this action, our new model will be like others. Save the result in STL file format. We will reduce the number of data points in it so that its size will drop from roughly 100 megabytes to below 1 megabyte by 2 orders of magnitude. You can use adekoCAM for the purpose by simulate reduce function, but in case your simulator is not adekoCAM, or in case the reduce function of adekoCAM over reduces such that the final model starts to have some defects after reduction, I'll also show you how to simplify the STL data using an open source tool called Blender with varying reduction ratios you can change. Start Blender and import the STL we just saved from within adekoCAM. Select a door and switch to the edit mode. As you can see, STL data has a lot of unnecessary points. This makes the file unnecessarily large. Use mesh cleanup decimate geometry function. Go to the small function configurator and enter 0.01 as the reduction ratio and press enter. This ratio is kind of okay for this model. In case your model has a lot of details, you might need to increase this number, as it might mean oversimplification which would distort your final model surface. Or in case your model has less amount of details, you might be able to enter even a smaller value like 0.005 for smaller file size. As you can see, the number of data points in orange dropped significantly. Switching to object mode once again and have a general look if the surface of the model looks okay. In case of over-reduction, you would see distortions on the door surface. Now we can override the original STL by File Export STL. Close Blender and restart adekoCAM. Go to the door interface by right-clicking on the project card to create an instance from this library, or go to door library from the top right door library to manipulate library items. In both cases, the library functions will be the same. Right-click on the model and select Show 3D Model, and as you can see, the model became available. Fit the image and click on Set as Model Image to take a snapshot of it. Right-click on the model icon and select Librarian, Change Image, and find the image just created, or restart adekoCAM. As you can see now, the model image is available. Now we can use this model as any other model, populating the list of doors and adding them to the project card. Here are some doors created out of our new model. In this longish video, we learned how to program a door model from scratch and how to make it a regular member of our door library. We did not set up its model parameters and open them to the library users though. This will be in another video. We also had some experience with conducting CNC simulation with adekoCAM to see the end result, reducing STL data size with Blender, and creating and setting up model images through the embedded door interface of adekoCAM. To know more about the door and product programming interface of adekoCAM, you can read the models of other designs, that is the script.lua files, or you can refer to the documentation on programming interface. You can also have a look at the math libraries of Lua library directory in adekoCAM's root. In these sources, you will find explicitly all the functions available for programming door and multi-part products, as well as the parameters they take. Thanks for your attention and perseverance.